Okay, so let's talk about some mechanisms of addition reactions to alkenes. I'm going to begin with an unsymmetrical alkene in order to show the effect of regiochemistry. So regiochemistry will be when I add, let's say we add HBr across a double bond. When it is not a symmetrical alkene, when there is a difference between carbon 1 and carbon 2, which of these carbons gets the hydrogen, which of these carbons gets the bromine? In order to really answer that question, you got to investigate the mechanism. So the last time we discussed this, we talked about 4 continuing patterns in mechanism. Those patterns were nucleophilic attack, loss of a leaving group, proton transfer, or rearrangement. So let's look at the alkene as a nucleophile, and let's look at HBr, where the hydrogen is an electrophile. Anytime you have a strong acid like HBr, the nucleophile will not be the Br. The electrophile will be the hydrogen atom. So the first step of this mechanism, the pi electrons in the alkene will make a bond with the hydrogen, and the HBr bond will be broken, and those electrons will reside with bromine. Of course, there were already 3 lone pairs on bromine. The result of this reaction leaves us with a choice as to which of these carbons will attach itself to the hydrogen atom. We could attach it to carbon number 2, which would leave a carbocation at carbon number 1. Or we could attach the hydrogen to carbon number 1, which would leave a carbocation at carbon number 2. If we start investigating hyperconjugation, we should quickly realize that we have a primary carbocation versus a secondary carbocation. Because the secondary carbocation gets orbital overlap with the empty p orbital from 2 carbon-hydrogen bonds, it'll be more stabilized via the inductive effect. Again, we call that hyperconjugation. And the secondary carbocation will be the preferentially formed carbocation. You can look at the potential free energy diagram and do a quick analysis of activation energies to validate this result. So I'm just going to show potential energy as a function of reaction progress. This would be the formation of the primary carbocation. This would be the formation of the secondary carbocation. Much more feasible to form the secondary carbocation because the energy of activation is so much lower as compared to the energy of activation, which would lead to the formation of the primary carbocation. Not only that, but anytime you would obtain primary carbocation, it would quickly rearrange to give the secondary carbocation. So the secondary carbocation will be what is preferentially formed. So as we continue our mechanism, I'm simply going to consider the secondary carbocation. I want to explicitly draw a hydrogen atom because this will become relevant. I can now have a rearrangement to make an even more stable carbocation through a 1,2 hydride shift. Remember, hydrogen and its electrons will break their association with the tertiary carbon and make a new association with the secondary carbon. What this accomplishes is a carbocation that now has even more hyperconjugation stabilization. Finally, Br minus, which we generated after the proton transfer step, now alleviates the charge on the carbocation through simple nucleophilic attack. And now this leaves us with a tertiary alkyl bromide. We can map this on a potential energy diagram. And I think really you should get in the habit of doing this for every mechanism that we learn from this point out. Carbocation, rearrangement, nucleophilic attack. Here's our product. And I'm gonna put all the transition states in one color to emphasize a little continuity here. So in this transition state, I'm making a carbon-bromine bond. The bromine is partially negatively charged, while the carbon is partially positively charged. In the second transition state, I'm showing a rearrangement of the hydrogen from carbon 3 to carbon 2. And this carbon will have a partial positive charge. Hydrogen would have a partial negative charge. And in the first transition state, pi bond is breaking, carbon H bond is being made, hydrogen Br bond is breaking. The bromine has a partial negative charge, while the secondary carbon has a partial positive charge. So those are my transition states. Let's now look at intermediates. And of course I'll render those in one color as well. So tertiary carbocation intermediate, secondary carbocation intermediate, And we'll go reactants. And we already have our products. Y-axis will be potential energy, and the x-axis will be our reaction coordinate. Quite simply, the progress of the reaction starting at time equals 0 until equilibrium is established and we've maximized our product yield. So transition state 1, transition state 2, transition state 3, intermediate 1, intermediate 2, products, reactants. The rate limiting step should be the formation of the secondary carbocation. So that's the energy of activation of the slow step. So as you can see, you can really do a very detailed job of mapping out this mechanism. In fact, doing the potential energy diagram requires more detail than the arrow pushing mechanism. Be prepared to do both of those. All right, so let's look at a new type of electrophilic addition reaction. Now let's look at the acid catalyzed addition of water to a double bond. So our reagents will be H2O and HCl. In the first mechanistic step, we will have a proton transfer. Pi bonds abstract the hydrogen. Hydrogen-chlorine bond breaks. I have generated Cl-. This will become important in the last step of the mechanism. And of course, as we've already seen, we'll generate a secondary carbocation. This secondary carbocation can and will rearrange through a 1,2 hydride shift. Usually over the arrow you'll write the shift. To yield the more stable tertiary carbocation. Now we're going to have a competition for nucleophiles. We already know that we have Cl- that we've generated, but we also have H2O as an initial reactant. So we have H2O versus Cl-. In order to determine which of these is a stronger nucleophile, you got to examine the conjugate acids. Hydronium with a pKa of -1.7 and HCl with a pKa of -7. Lower the pKa, the stronger the acid. So HCl is the stronger acid, which means hydronium is the weaker acid, which means H2O is the stronger base. And in aqueous solution, that also means strongest nucleophile. So it's H2O, more specifically the lone pair of electrons on the oxygen atom, that is going to attack this strong electrophile and its empty p orbital. This sets up yet another intermediate in which oxygen is positively charged. Remember, we had generated Cl- in solution, and now that Cl- will deprotonate to neutralize all of our species. So now we'll have HCl as a regenerated catalyst. We will also have the tertiary alcohol. Again, I think it's useful to look at the potential free energy diagram. That has got to be the worst drawing I've ever made in my life. I did not do well in kindergarten, but it was a playa, yo. All right. Yeah, should have paid more attention in kindergarten. Now, this time we have 4 intermediates. Excuse me, 4 transition states, 3 intermediates. First transition state is when I'm beginning to break the pi bond. And to make a CH bond. And to break the HCl bond, so that the chlorine is partially negatively charged and the secondary carbon is partially positively charged. Second transition state is when I'm going to begin to show the rearrangement. Partial negative on the hydrogen and a partial positive on the tertiary carbon. Next, I will begin to show the bond being made between carbon and the oxygen atom of water. And the last transition state will show the bond breaking between oxygen and one of the hydrogens, and bond making between one of the hydrogens and the chlorine atom. Now going to our intermediates. Secondary carbocation, tertiary carbocation, protonated alcohol, product, course, remember we also have HCl. Reactant. And of course we have potential energy versus reaction progress or reaction coordinate. Again, the energy of activation is the formation of the most unstable of our carbocations. So this is the energy of activation of the slow step. So in the slow step, we have two molecules. We would write the rate expression as rate equals K, concentration of the alkene times concentration of HCl. Notice the catalyst can appear in the kinetic step. It does not appear in the stoichiometry. So this should give you a nice head start in terms of attacking the problem sets. I'm going to also podcast the addition of Br2 across the double bond and also a little bit on the nucleophilic addition.